Hello, today we are going to solve the time-independent Schrödinger equation with a central potential. A central potential, U of r, only depends on the distance r from the center. We are going to work in spherical coordinates r, theta, and phi, and the Schrödinger equation, the time-independent Schrödinger equation, is Laplacian of phi. Now I'm using this phi for the time-independent wave function, and this phi written in this way with the azimuthal angle. So we have the Laplacian of phi plus 2m divided by h bar squared times w, the energy parameter, minus u of r, our potential, equals 0. Since we are working in spherical coordinates, we are going to expand the Laplacian in spherical coordinates, and we get dou squared. Now this symbol doesn't have a name, I just call it dou, and dou squared phi on dou r squared plus 2 divided by r. I don't remember the expression, so I'm reading it from here, plus 1 over r squared sine squared of theta times sine of theta dou in dou theta or sine of theta dou of phi in dou theta plus dou squared phi on dou phi squared, and don't confuse these two phi here, plus 2m divided by h bar squared w minus u of r times phi equals 0. This one is exactly our energy term, and this is the expansion of the Laplacian of phi. To solve this equation, we are going to use an ansatz. We are going to assume that we can write phi as a product of a function a depending only on r, b depending only on theta, and c depending only on phi. So we are going to assume that we can factorize phi in 3 independent terms. Now we're going to plug this inside the equation, and let's see what we get. Let's plug in. We get d squared of a on dr squared bc plus 2 divided by r dA on dr times bc plus 1 over r squared sine squared, I will write s I will write s for sine of theta for simplicity, times s. Now we can take the total derivative of sine if we because here we have to be in d theta, and we can take out from the derivation a and c, plus derivative squared of c in d phi squared ab. We want to obtain isolated terms, so we are going to multiply everything by r squared and divide by phi, so a, b, c, and we write that here. Plus the energy term equals 0. The energy term is this. I will not rewrite that now here, and so we have 1 over a d squared a on d r squared times r squared plus 2r divided by bc a, sorry, bc is already here, so divided by a dA dr plus 1 over s squared, because I multiply by r squared, times, and inside I will divide by ABC, so s, the derivative in d theta of psi dp on d theta, and this is divided by a, plus 1 over c d squared c divided by phi squared, plus the energy term, which is 2m divided by 8 bar squared times r squared w minus u of r, and I have divided by phi, so this equals 0. Now this term contains only theta and phi, and these two terms contain only r. So now I'm going to put together these two terms, r squared, I put outside r squared divided by a, so I get d squared r, d squared a on dr squared, plus 2 over r dA on dr, plus 2m divided by 8 bar squared a times w minus u of r, and then I leave this term as it is. So we arrive to this equation, which have two terms, one dependent only on r and one dependent only on theta and phi. We can write now this equation as like this. This equals minus this, so we have this term depending only on r equal to a term depending only on theta and phi. So this term as a whole does not depend on r, so it is a constant, right? Because it depends here only on r, but it is equal to a term which is not dependent on r. So I can write it as a constant, and by convention this constant is written L times L plus 1. So now we have two equations. We have separated our equation, depending on three variables, in two equations, one depending only on r and one depending only on theta and phi. We had this equation depending on r equals L times L plus 1, and this equation, this term depending only on phi and theta equal to L times L plus 1. So now we have two separate equations. Now let's concentrate on the equation for theta and phi. We are first going to study the angular equation. And we rewrite it like this. We put everything in there and we multiply by sine squared theta, so we get this plus sine of theta divided by a, d in d theta of sine of theta d in d theta, plus 1 divided by c d squared c on d5 squared equal 0. So we get to this equation, and we can now separate even this equation, because this term depends only on theta, this term depends only on phi. I can write this as this equals minus this. So each one of these terms must be equal to the same constant, and this constant is by convention written as ml squared. We have written L here to emphasize that there is a dependence here on L. Now let's concentrate on the equation for phi. and we write it like this. We put everything to the right and we multiply by c, and we get this second order linear total differential equation plus c of let's write ml squared times c of phi. This is one of the most simple second order linear differential equations, and it has very simple solutions. When L is different from 0, it has a general solution. C of phi equals C plus, right here, C of phi equals C plus a constant C plus exponential of I m L phi plus a constant C minus exponential of minus I m L phi. Instead, for ml equals 0, it has a degenerate polynomial solution. C of phi equals C0 plus C1 phi. Now, going back to the physics, remember that phi is the azimuthal angle, so it is periodic of 2 pi. So if we do a turn of 2 pi, we are representing the same point. So, for example, if I take this equation and I make a turn of 2 pi, you see that I get different result for C. But how can I get different results if I am exactly in the same point, right? So I can only accept solutions which are also periodic of 2 pi. So, for example, in this case, I can't have this term with phi, I can only have the constant term, because the constant term then is trivially periodic. And instead, concerning this solution, when is it periodic of 2 pi? Let's see, we have an imaginary exponential, so we have sinusoidal functions with ml phi, and they have period 2 pi divided by the modulus of ml. So the whole solution will be periodic of 2 pi when this is a submultiple of 2 pi, because in that case, if we do a turn of 2 pi, we have exactly the same value. And so this works for any integer ml. So ml must be an integer. So now we have these two equations, this for ml equals 0 and this for ml different from 0, but we see that if ml equals 0, this case is actually part of this, and this is contained in this case, in which case if ml equals 0, the constant C0 will be simply C plus plus C minus. So we have this general solution with ml an integer number. So this is our general solution for the azimuthal part. Now that we found a solution for our azimuthal equation, we go back to our polar equation. Now I write it in another form, multiplying everything by b and dividing everything by sine squared. Remember that with s I mean sine of theta, it is just faster to write, and we get 1 over s derivative in d theta sine dv in d theta plus L times L plus 1 minus ml squared divided by s squared times b equal 0. Now I do a change of variable, x equals cosine of theta, and so I get, when I do this derivative, where the differential d theta is the differential dx times the derivative of x with respect to theta, which is minus sine of theta. So I get this instead of this. So I substitute here and I get 1 divided by sine times minus sine, which is minus, and the in dx of sine d in d theta is this, so I get minus sine squared d in dx. The minus sign cancels out and I write s squared equals 1 minus s squared equals 1 minus x squared. So I get in the end d in dx of 1 minus x squared times db in dx, and this is 1 minus x squared d squared being dx squared. I'm using the chain rule, plus the derivative of this, which is minus 2x db in dx. So I can substitute this term here and I get the equation 1 minus x squared I'm using nothing times d squared b dx squared minus 2x db on dx plus L times L plus 1 minus ml squared divided by 1 minus x squared times b equals 0. So I get to this, which is a very well-known differential equation in mathematics. It is called the Legendre equation. The solution can be written in terms of the Legendre polynomials, like this: b of theta equals the Legendre, b1, a constant, a complex constant, times p LML, which is the Legendre polynomial of first kind, times cosine of theta, plus b2 times q and LL of x, which is the Legendre polynomial of the second kind, times cosine of theta. Anyway, most of these solutions are not acceptable because this expression must not diverge when x is equal to plus or minus 1, which means that theta is equal to 0 and pi. And we have that this term here diverges for the values plus and minus 1 of x. So we must have b2 equals 0. So we only have this part. And this term here only converge in 1 and minus 1 only if L is greater than 0, L is an integer, and L is greater or equal to the modulus of ML. So we have this solution for the polar part of the wave function with these conditions. In particular, there is an expression for a well-known expression for the Legendre polynomial of the first kind, which is PLML of x equals 1 over 2 L times L factorial times 1 minus x squared times ml divided by 2, to the ml divided by 2, and the derivative of order ml plus L of x squared minus 1 to the L. So we get to this expression for the polar part, where this is a conventional normalization constant, which is B1, and we have written it like this. Instead, for the azimuthal part, conventionally we put C minus equals 0 and C plus equals 1, so we get exponential of I and L phi. So we can put together B of theta and C of phi in Y of theta and phi, and this is the angular part of our wave function. So this is our expression for the angular part, and these functions are called spherical harmonics, and the modulus squared of this function of theta and phi and L times the angle differential sine of theta, this is the solid angle sine of theta d theta d phi. This is the probability to find the particle in the solid angle defined by d theta and d phi, so d theta and d phi. So if this is d theta and this is d phi, and then this is the solid angle, this is the probability to find the particle, this is the center, the probability to find the particle in this region here, which extends to the infinity. Clearly this does not depend on the potential U, because it is a central potential. The central potential only depends on the distance from the center, and it is independent on the orientation, and here we get rid of a particular distance of the center because we are getting all the distances from the center, given that the orientation is inside this solid angle. So with just this function and these conditions here, we can find the probability to find a particle in a particular direction. Now that we solved the angular part, we go back to our radial equation, and we're going to solve it for chi of r equals a times r. So we're going to substitute a equals chi of r inside, and the derivatives become the a in dr is 1 over r d chi in dr minus 1 over r squared chi. The second derivative, d squared a in dr squared, is minus 1 over r squared, this plus 1 over r, this I'm using the chain rule, plus 2 divided by r cubed chi minus 1 over r squared d chi in dr. So now we substitute them here, we get this is minus well, this would be multiplied by 2 over r, so we're going to do it here, 2 r squared 2 r cubed, and then the r added together, and we see that this this cancels out with this, and this cancels out with this plus this, and we are only left with this. So this is why we did that substitution, and we arrive to r squared divided by a times we are left only with this, so 1 over r d squared chi dr squared plus the energy term w minus u chi divided by r minus L times L plus 1 equals 0. Now we want to get rid of the coefficient in the second order term, so we're going to multiply everything by a times r, a divided by r squared. Then we multiply everything by r, and we get this. I forgot to substitute this a divided by r is chi divided by r squared, and then I take out chi, so we have g squared chi with gr squared plus, I take out also this, so I get w minus h squared divided by 2m r squared times L plus 1 minus u times chi equal 0, and this is our differential equation for chi. Now I simplify it by writing k squared instead of the energy parameter. K squared is 2m, that's by h bar squared with the angular momentum squared divided by h bar squared, and then I write small u equals the same thing, 2m divided by h bar squared big U, so I get d squared chi on d r squared plus k squared minus L times L plus 1 divided by r squared minus u equals 0. Sorry, times chi equals 0. So this equation for a central potential U of R, we determine our solution chi of R, and the total solution for this partial part of the wave function will be phi r theta phi equals psi of r divided by r, remembering that chi is r times a, so a is chi divided by r, times the angular part, the spherical harmonic L and L of theta and phi, and this chi is also parameterized by L and it is also parameterized by the energy W of the momentum K, so we write chi K L and L. So this is our general solution, and depending on the potential we have some acceptable solutions and some solutions which are not physical or non-normalizable. For example, if we have a Coulombian potential like in the hydrogen atom, we will have solutions only for discrete values of k. So we will have a discrete spectrum of solution, and we will have an equation k or n equals 0 relating k to a discrete quantum number n, which will take only integer values. And in the case of a Coulombian potential, it will take values from 1 to 3 and so on. This is why we have only discrete quantum numbers for the electrons in an atom, and in this case the function k l m l, instead of k we write it with the number n, phi n l m l. So for electrons interacting with a central potential, n will be a number related to the energy, L, which also appears in the radial equation, will be a number related to the shape of the orbital, and ml will be another number related to the angular part of the wave function. So I think this is enough for today. See you next time. It has been a pleasure.